as you see from the title slide, I'm actually not going to talk about the past, but only about the present and the future. But that's a bit, okay, that's the trick. Could I get a quick show of hands who knows what Flink is and maybe has worked with Flink? Okay, because I'm not going to talk a lot about what that is, but I hope you still get something out of this talk. So Flink is, at the core, it is a distributed framework for data processing. And what we highlight is that it is distributed processing with stateful computations of streams. And Flink has different use cases. So it is used for batch processing, meaning data that is sitting somewhere and is static and you want to produce some results. It is used for stream processing, meaning live processing of data as it comes in. And the special case for that is event-driven applications, where you have an application sitting somewhere and you have events coming in. That might be, for example, tweets, or that might be rides happening on Uber, or that might be users using Netflix, and you want to somehow react to these events. This, in a nutshell, is what Flink is. And going a bit deeper into where Flink sits into an ecosystem, if you will. So usually you have your applications, you have your devices, you have anything that produces data. This data can then be forwarded to a data bus such as Kafka or something like Kinesis, things that we call usually streaming data bus systems. It can be put into a database, or it can be put into distributed file systems or file systems. So that's where you have your data. And then Flink sits in the middle of the infrastructure, and it is basically the compute part or the processing part. And it can read from all those data sources, from streams, from files, from databases. It can emit data, like results of computations, again to streams, to applications, to S3, to Redshift, for example, to Elasticsearch, to Cassandra, Kafka, and what have you. This, in a nutshell, is what Flink is. And now I'm going to talk about some of the new features, the exciting new features that will be coming up in Flink 1.5. So Flink 1.5 is happening right now. There's a release candidate out. It should be released in the next couple of weeks. And after that, I'm going to talk about some new features that we have in mind that we might want to work on. So new in Flink is a big reworking of the distributed core of Flink. So that's what we call Flip 6. So Flip is short for Flink Improvement Proposal, and Flip 6 was a design proposal about how the distributed runtime of Flink should be reworked, and the reasons why we want to do this rework, or what we want to achieve with that, is a tighter integration with resource managers such as Yarn, Mesos, or Kubernetes, and to enable dynamic resource management so that Flink can go to these resource managers, dynamically request resources when it requires them, giving back resources. And also, as part of Flip 6, we did rework the interface that Flink exposes to the outside world. So before, that was a custom communication interface using Akka, and now there's a properly defined REST interface that users can use. So that's Flip 6. Another big feature is what we call localized failure recovery. So Flink, as I said, is a stateful distributed processing system, meaning it is running on multiple machines, and these machines, they have state. And in a distributed system, failures can happen. And when these failures happen, the system somehow needs to recover from that. And what Flink traditionally uses is it periodically does checkpoints to a distributed file system, and then when a failure happens, it can roll back the state of all these distributed processes running on different machines to this checkpoint. But this is somewhat costly, because when a failure happens, you have to reread all that state from a distributed file system, and localized failure recovery fixes that. So here, Flink stores some state on the machines where the computation is running, and when a failure happens, it tries to restart computations on the machines where that state is already available, and so can restart faster and doesn't have to reread state from the distributed file system. Another interesting rework is that we refactored, if you will, the network stack. So there was a 50% rewrite. This is quite low level, but what it will lead to in the end is that in streaming systems, there's often a trade-off between latency and throughput. So if you want to have high throughput, you often get very bad latency. But if you want to have good latency, you often don't get good throughput. But with this rework, we think that we are pretty good at providing very good throughput and also very good latency and improved back pressure handling. So that was kind of the low-level systems features that are new in Flink, and this is more on the API side of Flinks. So the first one is a new kind of API that we provide, or a new kind of stream where you can broadcast a stream to multiple operations and then have state in these operations. That sounds kind of technical, but what it enables is use cases where, for example, you have a stream of data that you want to process, but you don't before that know what the computation you want to perform on that is. But using broadcast streams, you can send computation or rules into an operation on a side stream and use that to process the incoming data on the main stream. This is the use case that this enables. Another very exciting feature is the new SQL CLI. So traditionally, when you were writing Flink programs, you would have to write Java programs. So that means using this Java API that we provide for data streams or for data sets, similar to how you would use the Spark API, for example. So that has a bit of boilerplate, and not everyone likes Java, and data scientists don't usually are very familiar with those kinds of things. So writing SQL is something that a lot of people can do, and it's also a thing that, for example, analysis tools can generate. And Flink in 1.5 has this new SQL CLI, which is an interactive command line interface where you can just input queries, and then Flink will do the rest and basically take this SQL query, generate a Flink program from that, execute it, and generate results. And one thing that makes this possible is the next point, actually, is unified table sources. So in a data processing system like Flink, you have to have a way of defining sources of data. So that's Kafka, as I mentioned, or files. And you have to have a way of defining sinks where you write data to. And this work that we did is about having a unified way of defining these sources. For example, when you run a SQL program, you don't want to write Java code that defines the source that you want to have, but you want to write a simple property-style configuration where you can tell Flink what the source is and where the data is coming from, what the schema is, and so on. And the last thing that I want to highlight in Flink 1.5 is something that might sound a little bit boring, but it is that we did a huge push with regards to automated testing and automated release verification, because in the past, Flink releases have sometimes been delayed because there's a lot of manual work that we're doing for each release, where we have huge checklists of things and programs that we try out and running things on a cluster, which delays a release sometimes. And here we did a push of writing a lot more automated tests that make sure that we can quickly do Flink releases. So for people that know, for example, we now have tests that use Jepsen to do failure injection and verify correctness of Flink. So that's it for the present, so the soon-to-be present when Flink 1.5 is released. And for Flink versions beyond that, the stuff I'm going to talk about is a bit more out there. It's a bit more experimental, or we don't have yet a clear view of what we want to do, but these are a couple of things that we have in our heads. So the first thing is auto-scaling. So in Flink, you have your program running on a set number of machines, and when you start your program, this is the number of machines that you will have until the program finishes. So say you want to run it on 10 machines, that's what you're going to get. But if then you see that actually this was way too much, or this was maybe too little for the amount of data that you get, then there are ways in Flink to stop the program with the state and restart it on a different parallelism. But a nice thing to have would be that you can specify policies that Flink would automatically detect whether it should increase the number of resources or decrease it, and then automatically adjust the parallelism or the amount of resources it uses. Another thing is hot standby replication. This is also, again, regarding state. So as I said, when failures occur, you somehow have to restart the running program, get all the state back in, and then get the program running again. This can have a couple of seconds downtime or maybe longer downtime based on the size of the state. So the way we want to tackle that is by having hot standby replication, basically where we have more machines running than necessary, and they also have the state of the computation. And then when one machine fails, we can switch computation to one of these other machines. And also in this area of features is zero downtime scaling and upgrades, where basically if you have a streaming program, you want to run that 24/7. But at the same time, you sometimes want to update the frameworks of Flink, or you sometimes want to update your user code if you discover there's a bug. And right now what you have to do is you basically store your state, tear down the program, restart it on a new machine, on a new cluster with that old state, and then you continue. But here again, we are trying to come up with ways where you can do zero downtime updates and scaling. And as a last bit of new stuff that is coming up on the table API side, so this is the table API. SQL API is this thing for where you can run SQL queries, and we want to do more integrations with different data sources, integration with more databases, for example. And then even further out there, we want to do, right now there's a differentiation between the data stream API and the batch API, and have somewhat different algorithms because these use cases require different performance characteristics. But we would like to unify that so that the system can automatically detect, okay, now a batch execution style would be more appropriate because we are currently processing maybe old data before going over to live data. And then when we switch over to live data, we want to use a more streaming approach to processing. So that's how we want to do that. And what we also want to do is to provide support for more programming languages. So right now you can use Flink with Java and Scala. And we are currently working with the Apache Beam project, for some people that are aware of that, where we can provide Python support and Go support, which in turn would also provide support for running TensorFlow on Beam with Flink, so that you can do machine learning and in turn also API on top of Flink via Beam. So, wrapping up, I've been talking about all these features and the work that we have to do, but so this might sound like complaining or that stuff is not very good, but Flink is, in my opinion, is still the best open source stream processing system that you can use, and a ton of companies are using Flink in production since quite a few versions back. So yesterday there was a Flink Forward conference also here in San Francisco, and there a lot of companies talked about how they are productionizing Flink within their company. So that's sounds like it's complaining on a high level, if you wish, or the stuff that we have to work on is good stuff that we want to add. So basically, Flink is already good, but there's more cool stuff coming, if you will. That's it.